It does accelerate time. We can see basically a year's worth of real behaviour in the model in perhaps a little over an hour.
We are at the National Infrastructure Laboratory at the University of Southampton. This huge centrifuge is used to speed up time, condensing events that in the real world could take years or even decades, squeezed into a few minutes. That makes measuring long-term change highly efficient, saving huge amounts of money over conventional research out in the field.
Soil is perhaps one of the most difficult of all engineering materials to understand. So this lab behind me is dedicated to tests that we do on elements of soil to try to understand its fundamental engineering behaviour.
And with greater accuracy and reliability than before. This machine can take a 1-ton object and spin it at 130 times its normal weight. It can spin here at 200 times a minute. That is 138 miles an hour.
It accelerates time. So at a scale of 1 to 100, for example, we can see almost a year's worth of real behaviour in 1 hour of running in the centrifuge. The amount of money that it could save is probably in the hundreds of millions of pounds. You're looking at 1,000 or 10,000 times the payback for a series of tests that could easily be saved by making the design more economical.
Coupled with research in the Southampton laboratory, it is helping develop new, more sensitive ways of installing offshore wind farms.
We're looking at cleverer and more economical foundations for large offshore wind turbines, for example. So we've got a significant activity which can use the geotechnical centrifuge to understand how those foundations behave, and again how they can be designed not only more economically in cash terms, but also more economically in carbon terms.
The giant turbines are mounted on huge piles, hammered deep into the sea floor. Now, new ways of securing them in soft material are being tested.
The thing about the pile is that when you install it, it has to be hammered in, and this requires quite a high vertical force. It's also very noisy, so it causes a lot of disturbance and distress to marine life, so fish. Whereas with the screw pile, this can be installed in the ground via a twisting motion, which requires less vertical force. And it also is a silent piling technique. When you want to test these things under more realistic conditions, you need the centrifuge to do accelerated modelling. So in terms of stresses and forces, it allows us to scale up what actually occurs in the seafloor.
The centrifuge can help to assess long-term changes to the structure of railway cuttings and embankments, stresses and strains that can happen across many decades. By modelling what happens to the embankment, accurately predicting change, we can help prevent incidents like this. After weeks of heavy rain, extensive flooding undermined the railway south of Salisbury. The waterlogged embankment slipped away, bending the tracks, compromising safety. Putting it right disrupted tens of thousands of passengers. It took months and cost millions of pounds. Here in Kent, an embankment collapsed near Edenbridge. For weeks, the track was closed. Buses replaced trains. Here in Hampshire, an embankment collapsed near Alton. Engineers strengthened this Victorian earthwork with steel piles.
This is a sample box. It contains the soil model that we want to test in flight.
Now we can test soil structures more accurately than ever before.
For fine soils such as clays and silts, the sample would need to be spun for at least a day or two. Some tests can take days, some can take weeks. The longer duration tests would be, for example, modelling the effects of climate change on embankments.
If we have a model at a scale of 1 to 100, in the centrifuge at 100 times normal gravity, so that's at 100 G, 1 hour of running in the centrifuge is equivalent to just over a year in real time. So we can see the behaviour in over a decade in just less than 10 hours running in the centrifuge.
And when we build new railways or roads, or repair existing ones, we can better predict how structures will change over time.
What we want to do is check the impact of future extreme events and scenarios. It's obviously not possible to do that with what we have at the moment. That centrifuge facility gives us the opportunity of modelling and simulating future events, and then that gives us a basis for developing new designs and new infrastructure.
It helps us adapt to a changing climate with hotter, drier summers and more intense winter rainfall, altering the behaviour of structures that were designed long before anyone knew that could happen.
So we can simulate climatic changes in the centrifuge. We can simulate rainfall, we can simulate surface waters, and that's one of the exciting things that we'll be able to do, because nobody's really had to investigate that before. As we go forward and we see the impacts of increasing climate volatility, we are potentially seeing more failures of earthworks because of the interactions with rainfall and surface water. So we can investigate how that's going to pan out. We can develop new ways of doing the analysis so that infrastructure owners and designers can make sure that their cuttings, embankments and so on are safe for the future. But with climate change, we have the opportunity and the potential to look at how projected changes in climate will impact on our infrastructure without waiting for it to happen.
This state-of-the-art modelling can shed new light on practical problems that, until now, were difficult to analyse, reducing costs and improving efficiency, helping to make the world we build around us safer and more resilient to a changing climate.